Welcome back. In this video, we're going to continue to solve trigonometric equations. The very first one I'm looking at is tan squared x plus tan equals 0. Again, I'm solving this equation, so I would like to know what values of x make this equation true. All right, in the previous examples, we had a single trig function that we could isolate, set it equal to a number, and then we would just use our knowledge of trig to solve it. Here I've got more than one trig function flying around. But that's okay, I've got some tricks up my sleeve. When I first look at this equation, we call it a trigonometric equation because the variable is inside a trig function. But when I look at the equation, I think of a quadratic equation. This is something being squared, plus I've got like a linear term equals 0. That's what's going on in my head. So, replace those tangents with some other variable like z or something. If I had z squared plus z equals 0, if I had that situation and you asked me to solve it, I would think, oh, this is quadratic. In order to solve a quadratic, I would want to set one side of the equation equal to 0. I would kind of hope that it factors. If it doesn't, I could try like a quadratic formula or something like that. So my brain is going straight to factor if I can. So looking back at the tangents, oh yeah, this is a binomial. Both terms have tangent of x. So I'm going to factor tangent x from this binomial. If I factor by tangent of x, that's just a fancy word for division. Tan squared divided by tan is tan. Plus I'll have 1 here, and that's going to be equal to 0 still. So that's just, we could always distribute just to make sure we're on the same track. Tan times tan is tan squared. Tan times 1 is tan. Okay. Now that I have this factored, I have 2 factors equal to 0, so I can set each factor equal to 0. So the first factor equals 0, and tangent of x plus 1 equals 0. All right. Now I want to isolate the trig function. So on the left, I'm good, but on the right, I want that positive 1 to be on the other side of the equation. So I'll just subtract it over. All right, now I know these values. Tangent is 0 at 0. Let's see, let me get a unit circle out here. Tangent is the y value over the x value. Tangent of 0 is 0, and tangent of pi will also be 0. The y value is 0 divided by the x value, -1. Yeah. So over here, what makes this equation true is 0 and pi. For this equation, tangent is negative in quadrants 2 and 4. So that's going to be 3 pi fourths. And tangent will be -1 again at 7 pi fourths. All right, there are 4 possible solutions that will make this equation true within the interval 0 to 2 pi. Again, there's an infinite number of solutions out there, but I'm just going to list the first revolution of the unit circle. I'll put them in increasing order. So 0, 3 pi fourths, pi, and then 7 pi fourths. Those 4 radians will make that equation true. So the key for this example was to factor. Factoring got rid of that square for us. All right, my next example. I have, oh yeah, my brain goes straight to that quadratic feel to it. I've got sine squared x minus 1/4 equals 0. So I'm happy that one side of the equation is 0. Dealing with quadratics, that's kind of what we want. Yeah, I'm going to factor this one as well. Now I see two different ways we can handle this. Because there's no linear term, I could move the 1/4 to the other side of the equation, and I could square root both sides using a square root property. I have a lot of students, though, that will forget about the positive and negative result. So I'm going to stick within this factoring mindset. On the left-hand side, I have the difference. I can always factor that. I got the difference of two squares. So this will factor into sine of x plus 1/2 and a factor of sine of x minus 1/2. I kind of did that in my head real quick. Let me just distribute to make sure. Sine times sine is sine squared. Negative 1/2 of those and a positive 1/2 of those will cancel to 0. And then 1/2 times negative 1/2 is a negative 1/4. All right, two factors set equal to 0. I can set each factor equal to 0 and solve them independently. For both, I need to move the 1/2. On this first equation, I'll be subtracting. On the second equation, I'll be adding. So I have sine of x equals a negative 1/2 and sine of x equaling a positive 1/2, or sine of x equals plus or minus 1/2. So that's all of those pretty sixths values, the pi sixths values. On a unit circle, sine is 1/2 at pi 6. It'll be 1/2 at 5 pi 6, and then it'll be negative at 7 and 11 pi 6. So I have the set pi 6, 5 pi 6, 7 pi over 6, and 11 pi 6. Oops. These are the solutions within that first revolution of the unit circle that make this equation true. For this example, I saw that quadratic feel to it, and I knew I wanted to factor, especially with that 0 over there. Two factors equaling 0, you can set each factor equal to 0 and solve independently. All right, next example. Whoa, okay, I've got the square root of 3, tangent squared x, plus the square root of 3, tan x, minus tan, minus 1 equals 0. Okay, not too bad. If it helps, we could do what we did before, where we replaced those tangents with another variable. We used z. That may help you see what's going on. There's a lot going on. But again, I've got this quadratic feel to it. This is a tangent being raised to a second power. So my brain is going toward factoring. And I already have one side of the equation equal to 0. I'm on board. But I have 1, 2, 3, 4 terms. So I cannot use difference of squares. I don't see a GCF. That's what we did in that previous example. We took out a GCF, a greatest common factor of tangent. We pulled it out. In the next example, we did a difference of two squares. I saw the difference of two terms, so we used the difference of two squares. This time, and it's not a trinomial, so I've got 4 terms, nothing in common. I think what I can do, though, is look at them like such. So the first 2 terms have something in common. The last 2 terms have that negative 1 I could pull out. So if I have 4 terms, I could try factor by grouping. That is, I take a look at what the first two terms have in common and I factor it out. So ignoring that part. The square root of 3 is in common, I can factor it out. The tangent is in common, I can pull that out. I'm going to factor out the square root of 3 tangent x. And that will leave me with, it's just division, tangent of x plus 1. From the second grouping, these two terms, it has that leading negative that I would like to come out. So I'm going to factor out a negative 1. That's going to leave me with tangent of x, now positive, and now positive 1. This isn't technically factored yet, but I've got now a binomial, this thing minus that thing, and, oh yeah, this binomial has something in common. This binomial, tan x plus 1. So in my next step, I'm going to factor out this term, tan x plus 1, and that's going to leave me with this square root of 3 tangent x minus 1. Factor by grouping, we can try it when we have 4 terms. It worked because these two factors were the same, so I could continue with the process. And now I have 2 factors that when you multiply them together, they equal 0. So we can use this zero product property where we can set each factor equal to 0. So the first factor, tan x plus 1, equals 0. And then the second factor, the root of 3 tan x minus 1 equals 0. All right, now I can solve these independently. For the left-hand one, I want the plus 1 on the other side of the equation. I've got a now linear trig function, so I'm going to kick over the 1 to the other side. So I have tan of x equaling negative 1. On the right, I need to add the 1 over. And then the right one has a coefficient of root 3, so I'm going to divide that off. Okay, I know where tangent is negative 1. I even know where tangent of x is 1 over root 3. Now, this may not seem familiar to you, so if it doesn't, then rationalizing should. So I'm going to rationalize this denominator. I'm going to multiply top and bottom by root 3. So tangent of x is equal to the square root of 3 over 3. Now that should look familiar. That happens at those sixths values. So on the unit circle, tangent is negative 1 in quadrants 2 and 4. This sounds familiar. We have 3 pi-fourths and 7 pi-fourths. That's where tangent is negative 1. Tangent is positive root 3 over 3 in quadrant 1 at pi6 and quadrant 3 at 7 pi6. All right, I see 4 solutions to this equation. I'll just list them in set notation. I'm going to put them in increasing order. Just to recap, 4 terms, had that quadratic feel to it. I'm supposed to isolate the trig functions, so I tried to factor by grouping. It worked. So then I had 2 factors equaling 0. I set them both equal to 0. Solved those separate equations independently, and then I get 4 possible solutions that make this equation true. All right, my next example is I've got 2 times sine squared of x minus 3 sine of x plus 1 equals 0. Again, got that quadratic feel to it, so I would like to set it equal to 0 and kind of hope that it will factor. So it may, if you can't see that this is a trinomial that you have already factored 1,000 times, it may help to replace those trig functions with a variable, like we said earlier. In fact, I'm just going to rewrite this equation, but wherever I see sine, I'll replace it with that dummy variable z. So I have 2 times something squared minus 3 times that same something plus 1 equals 0. So this is just a trinomial. Several ways to factor trinomials, but I think I can just force it, just like a trial and error method. Trinomials should factor into the product of 2 binomials, where the first 2 terms, when I multiply them together, they have to give me 2z squared. So I think 2z and then another z. The last 2 terms have to multiply to give me a 1. Well, I'm going to use 1 and 1. This plus sign kind of leads in that these signs are going to be the same, and then this one tells me they're both going to be negative. Now I just did that in my head. That's a trial and error method, so I'm going to just distribute to make sure I got the right terms. All right, 2z times z is 2z squared. Negative 2z and a negative another z is a negative 3z, and then negative 1 times negative 1 is positive 1. Cool. Oh yeah. So then I can set each factor equal to 0 and solve. So it may help with these trig equations to think of them as just some variable to help you manipulate them. I'm going to go back to calling z sine. So this is 2 sine x minus 1 and sine x minus 1. You don't have to show that substitution process. I'm just showing it to help some students visualize trig as just a variable, just some thing. Now in this form, I'm extremely happy. 2 factors equaling 0. This is rinse and repeat. Set each factor to 0. Isolate the trig function. Solving 2 at the same time. So kick over the 1, divide by 2, kick over the 1. Sine will be positive 1/2 in quadrants 1 and 2 at pi 6. And at 5 pi 6. Sine will be positive 1. The y value is 1 at pi halves. And that's it. So I see 3 solutions within the first 360 degrees. There we go. So these 4 examples were all factor, 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 factor. Yeah, lots of factor. All right, next example. Well, straight off the bat, I see the difference of 2 squares, but I don't think I'm going to factor in this one. I've got cosine squared x minus sine squared x equaling 1. So if I tried a difference of 2 squares, I would not have 0 on the other side of the equation. So that wouldn't help me. I had to have a 0 there. So I could move the 1 over, but then I no longer have a difference of 2 squares. All right. Oh, in fact, I don't think I've had this situation before where I have 2 different trig functions. Wait, okay. I think what I would like to do is use an identity, some trig identity, to maybe rewrite one of these trig functions as the other. So, like a Pythagorean idea. Pythag says sine squared plus cosine squared equals 1. So let me write that off to the side. We know sine squared an angle plus cosine squared an angle equals 1. So what I would like to do is take this cosine squared and rewrite it in terms of sine. So I'm going to go off and solve that identity for cosine squared. Basically just subtract sine squared from both sides. So cosine squared x is also equal to 1 minus sine squared x. I'm going to make that substitution. Cosine squared x can be rewritten as 1 minus sine squared x. Now this is not the only way to solve this equation. I also see on the left-hand side, this looks very familiar. It looks like a cosine double angle ID. We could try that. That would get rid of the sine altogether. We'd have cosine 2x equals 1. I bet we could solve it like that. But I saw first a Pythagorean, so I'm just going to replace cosine with, rewrite it in terms of sine. Now I've got like terms that I can add together. I have 2 of these sine squared x's. I'd like to isolate the trig function, so I will, let's see here. I think I'm going to take the negative 2 sine squared x and add it to the right, and then I'll subtract the 1. In fact, the 1s are going to go away. Let's see if you like this. Just doing a lot of rearranging. Ones cancel each other out, and I've moved that to the other side of the equation so that 2 sine squared is now positive. Now I need the coefficient to go away, so I will divide both sides of the equation by 2. 0 divided by 2 is still 0. I think now I will, I'm trying to isolate the trig function. So I've got sine squared. So I will square root both sides, I suppose. Now that's okay as long as I remember there are positive and negative results. This is kind of a bad example for that, but I've got a positive and negative 0 to worry about, equaling sine of x. So the square root of sine squared should just bust out as sine of x. If that were some other value like 1, I would have to worry about a positive 1 and a negative 1 result. If that were a value like 4, I would have to worry about a positive 2 and a negative 2 result. Because it's 0, I don't have too much worries. Positive and negative 0 is just 0. Okay, so I'm just trying to answer the question, sine of what would give me 0? Well, I know that happens at 0, and I know it happens at pi. So this one was not factoring. This one was using some identities to rewrite the equation into something that I could solve. So if you ever see these squares, that's a key that probably Pythag is involved. So like tangent and secant, those squares go well together, and then cosecant and cotangent, that's probably a good strategy to employ. All right, that's solving trig equations, at least the basics of it. So good luck, and I hope that helped.